In this video, I'll be going over the precise definition of a limit. Now this time, I'm going to be going over a linear function, which we can see over here in this function. Remember that inside over here, after my laptop decides to do better, we have, so basically our standard form for our limit is x approaches a of any function, which is equal to our limit value, right? And in this case, this is our function value over here. Okay, and then this negative 11 will be our limit value, and then this over here, this negative 2 is our a value. Okay, now what do we know about our definition of a limit? I can go through the full explanation again, but if I do that, then basically I'm just going to be going over the same video that I've already made initially, which was explaining the precise definition of a limit. So we need to actually state what is the precise definition of a limit. It states that for every epsilon that is greater than 0, there exists a delta which is greater than 0 such that we have the absolute value of x minus a is between delta and 0, which tells us that absolute value is between 0. So absolute value of f of x minus the limit value is less than our epsilon. Okay, so that is our standard definition. Now what we need to do is obviously we need to link this question to our definition so that we can answer it. So what are we going to do now? So because we show that, right, we are given that we have the limit as x approaches negative 2 of, it was 4x minus 2. Was it 4x minus? No, 4x minus 3 is equal to negative 11. Now obviously we know if we do directly substitute this negative 2 into the function, we will have 4 multiplied by negative 2 minus 3, which will give us 4 multiplied by negative 2 is negative 8, and then we have minus 3, which minus 8 minus 3 is going to give us minus 11. So that means this is true. But we need to use the precise definition of a limit. So this is how we're going to start. Now we're going to state over here, for every value of epsilon that is greater than 0, there exists a delta also greater than 0, such that, I'm just going to write st, such that the absolute value of x minus our limit value over here, which is negative 2. Sorry, not our limit value, where x approaches, it's negative 2, so we're going to write that in the bracket there, which is between epsilon and 0. And this implies that we have the absolute value of the function, which is the function that we have is 4x minus 3, so I'm going to write it in brackets, 4x minus 3 minus, and then we're going to have the limit value, which is negative 11, is going to be less than epsilon. Alright, so where do we start? First of all, we want to actually know which delta we must choose, right? We need to choose a delta, but how do we do that? First of all, we need to look at this. So we're going to put this on the side. We need to choose a delta. Now, over here, we're going to do the following. We're going to say the absolute value of 4x minus 3. Let me just get rid of the bracket. And now we're going to actually simplify this. So this negative and a negative gives a positive, so that's going to be positive 11. Is going to be less than epsilon. And then we have to simplify this one over here. And then we are going to get 4x. So 4x is still a term on its own. Then we have negative 3 plus 11, or we can say 11 minus 3, which is equal to positive 8, which is less than epsilon. Okay. And now from here, what we can see is we have common factors of 4. So we can take out 4 as a common factor, and then we have x plus 2 is less than epsilon. Now one thing I didn't really do was actually simplify this over here, which I took I'd have to take the negative in. So if we take the negative in, a negative and a negative is a positive, which is positive 2. So now it's actually going to be x plus 2. I didn't even do that initially. So we have x plus 2 is between 0 and delta. So because of that information, we can actually see, oh yeah, no, we have to actually get absolute value of x plus 2 on its own. So we have to divide both sides by 4, such that these will cancel, and then this will be absolute value of x plus 2 is less than epsilon over 4. All right, and what else do we know about this, right? What we know is that the absolute value of x plus 2 is actually over here, which is less than delta. Meaning, because that's less than delta, and it's also less than epsilon over 4, then therefore we can say that delta, so we can say therefore our delta is also equal to epsilon over 4. Now because of that, also, by the way, this is not the correct notation. How you're actually supposed to represent it is, therefore, we choose our delta to be equal to epsilon over 4. That's how you represent it. Remember, it's a proof. You can't just write down random things. Now, from this information, we're going to go back to whatever we had over here, right? This thing. But we're only going to look at this absolute value. And this is how we're going to write it down. Right? So we start here. It's going to be the absolute value of 4x minus 3 minus 11. And now we're going to have to evaluate, right? Well, not really evaluate. We're going to have to simplify. So over here, what we know is this is going to be equal to, we just have to simplify. We're going to have 4x minus 3 minus gives a plus. It's going to be plus 11. And that's going to be the absolute value over here. This is going to be equal to the absolute value of 4x minus 3 plus 11. That's just going to be plus 8. And then we can take out 4 as a common factor. And then we're going to have x plus 2. And now what we can see over here is that we have 4 multiplied by x plus 2, right? And what do we know x plus 2 is similar to? We know that x plus 2 is less than delta. So therefore, what we are going to say is that 4 multiplied by absolute value of x plus 2 is going to be 4 multiplied by delta. And the reason why we can say this is because obviously we have x plus 2 is, we know that x plus 2, or sorry, absolute value of x plus 2 is less than our delta. And if we, let's say for example, have something like, okay, we have 4, right? Let's say this was something like 4, and this would be less than our delta, which was supposedly bigger. 4 would be less than any number that's bigger than 4, obviously, right? So we can say that would be 8 maybe, for example. That could actually stay true. But if we say, or actually, sorry, I should actually do this. Let's say 5, right? Because that's a little bigger than 4. And if we multiply both sides by 4, something like what we have here when we're multiplying them by 4, then therefore we'll get 4 times 4, which is 16, and then we have 4 times 5, which is 20. And this stays the same in the same criteria. 16 is less than 20. And that is why we use the following over here, the following symbol for this. Okay, and then remember that we chose our delta to be equal to epsilon over 4. So that's what we're going to do. Now we're going to say equals, right? This 4 times delta is actually equal to 4 times epsilon over 4, right? Which therefore, these 4's will cancel out such that you'll get epsilon. And it works just like this. But remember, just to make the notation clear, right? Remember that we basically said over here that this absolute value, we evaluated, we still kept the equals correct, but then we said remember, this is exactly the same as this. But now we said that this is less than that, using this symbol over here. And then we evaluated this one over here by using the equal signs, which is equal to epsilon. So 4 times delta is equal to epsilon. That's what we're saying. So you can conclude that therefore we have the absolute value of 4x minus 3 minus negative 11, which is less than epsilon in our case over here. And then therefore the limit is going to be true. Therefore we have actually proven using the precise definition of a limit, that the limit is true.